Hello and welcome to this webinar jointly hosted by the National Physical Laboratory and the Institution of Mechanical Engineers. Thank you for joining us on World Metrology Day. On World Metrology Day, we're holding this webinar and we're launching a new report called The Power of Precision: How Better Measurement Drives Engineering Excellence. Before we get into the presentation, we've got a few housekeeping things to cover. We've got Q&A, so please do send your questions in along in the Q&A box. Just for information, the video will be recorded and will be available at a later date. And if you require subtitles, you can click on the CC button at the bottom. Not speaking today are Sarah Dalmado and Laura Kent, but I would like to pass on my thanks to them for all the work they did on this report. And my thanks to the National Physical Laboratory for working with us to get this report published today. We have a few speakers from the National Physical Laboratory. Later, we're going to hear from engineers Timothy Camps, James Berry, and Georgette Gaunt. But first, I'm going to hand over to Rob Smith to talk about the report. And just so you know, the report is available on the IMechE website in the policy and press section if you'd like to read it. Rob, take it away.
Thanks for that, Matthew. So yeah, if we could go on to the next slide, please. So I'm Rob Smith. I'm the head of engineering at MPL. It's okay, go on, skip on. So for those of you who don't know, the National Physical Laboratory was founded in the year 1900. So as well as being the World Metrology Day today, this is also our 125th year anniversary year. So a quick shout out to all of the open day events we've got going in a couple of weeks. If you're interested in any of those, please have a look on our website and you can see more details there. Now, MPL is a publicly owned corporation, so the Department of Science and Innovation and Technology is our owner, and we are primarily based in Southwest London in Teddington, but we have locations and staff dotted around the country in places like Strathclyde, Cambridge, Huddersfield, etc. And we also partner strategically with DSIT and the University of Surrey and the University of Strathclyde. Now, at the moment, we have about 1,000 scientists and engineers across a range of different disciplines and skill sets. And I think back in the year 1900, I think it was around 20 we started with. So the need for supporting industry in the UK on measurement has been growing continuously since then. So if I could ask you to pop onto the next slide, please. So engineering at the National Physical Laboratory is an interesting term because we have a range of scientists and engineers working across a whole different level of disciplines, with many people describing themselves as both. So my background is actually in physics, but over my career, I've worked more and more in engineering fields. So we have lots of engineers or people who consider themselves a bit of a physicist, a bit of an engineer or a biologist, whatever, across the whole lab. But we do have a centralized engineering function at MPL to try and provide expertise and support across everything the laboratory does. So this is from things like small little manufacturing jobs that might take a few hours, all the way up to supporting some of our major programs and bids and other activities we do. We're currently going through an improvement program on our engineering capability, aimed in a few areas, one around our processes and how we work. So a key thing here is we're implementing a product lifecycle management system to enable us to work in a lot more collaborative way across the laboratory. So this is the Dassault 3DX for those of you who might be familiar with it, but also allows a lot more efficiency in how we work, and allows a lot, hopefully, when we roll this out over the next few years, a lot more collaboration between different research groups, between different engineering activities, not just within MPL, but across all of our collaborative partners. A lot more on the digital engineering, model-based system engineering, all this sort of stuff that, the next generation of engineering activities we need to support. But more importantly, we're also looking at how we can recognize and support engineering as a distinct career pathway. So, how do we support our scientific and engineering communities in their professional development? How do we enable people who might have started their career as a chemist or another scientist but are interested in engineering? How do we support that activity for them in their development? but also how we offer access into engineering. So things like our graduate program. So we've recently started an MPL-wide graduate program, but how do we do something like that with engineering? And also importantly around our apprenticeship paths. So we have a very good engineering apprenticeship program, but how can we adapt that to the modern world and look at different types of apprenticeships, but also how we offer that up to level 5, to degree level, and other types of options that we can do. So rather than talk about just that, what I thought I'd do is try and cover a little bit of how MPL works before we hear from Georgette, James, and Timothy about some specifics in their area. So the work at MPL covers a whole range of TRLs and applications. And I've tried to pick one type of application where we can look at how we link the laboratory work that we do and how we have our primary standards, which I'll discuss a bit more in a second, to how they can have impact in a variety of industries and settings in the industrial or academic areas. The key thing I hope, though, from these examples is it really highlights how if you combine the best of the scientific approach to working and the engineering skill set and capabilities, you can maximize that. And that collaboration for me is the key to how MPL is successful, is that we can combine this breadth of experience and skills to progress things through that TRL range. And before we go on to the slides where we've got the pretty pictures, I just want to acknowledge in particular Paul, Chris, Josh, and Aaliyah, whose names are at the bottom, because I'm taking a lot of credit for all their hard work here. But obviously, there's a huge team even behind them. And I think that's the last point I want to make, is that especially these days, any advancements or delivery projects are team efforts. The ability for teams to adapt and grow and contribute in different ways is a key aspect of how we can deliver that impact and that revolutionary science and engineering. So if you go on to the next slide, please. So the cryogenic radiometer. So the cryogenic radiometer at MPL is something that we call a primary standard for one of the SI units, in this case, the luminous intensity or the candela. So a primary standard refers to something where we have an instrument that gives us direct measurement and allows us to calibrate things against one of those it's the pinnacle of the measurement pyramid. Anything else around optical power that we may work or measure to will reference back and be calibrated back to this cryogenic radiometer and the candela. And there'll be other ones at MPL for things like the meter or the second or the kilogram, when you hear about one of those in particular later on. Now, the cryogenic radiometer, I'm massively dumbing this down, so apologies to the science and engineering teams who worked in this, but you apply an optical signal onto a detector head, measure the response that it generates in terms of energy deposited effectively, and then replicate that response with a calibrated electrical signal. So you can calibrate the optical source back down to another reference and determine its luminous intensity. So you can see some pictures on the screen there of the cryogenic radiometer that we've had at MPL for a good few years now. And we've been using that as our primary standard, but there's been a need to upgrade that unit. And so we're in the middle of a design and build of the next iteration of that cryogenic radiometer. So if we could go on to the next slide. Like I said, we're currently manufacturing the components from this, so you're going to have to make do with a CAD model of it, I'm afraid. But the cryogenic radiometer 2, when we've approached that with this combined science and engineering approach, we wanted to try and take all the information that we'd learned from operating the previous design and build in how we can improve on it based on operational experience. We wanted to address obsolescence problems from the previous radiometer, but also as we're going through this process, be able to do some more detailed requirements capture, design risk assessments, FEMEA studies, et cetera, et cetera, et cetera. The other thing we wanted to do, though, is actually design something for manufacturers. So we wanted to look at how we could ensure that components we were using had longevity and support for manufacturers, use COTS items as much as possible, base the design on any proven technology we could find, but also implement things modularly, which would allow us to upgrade and improve the system in the future, but also enhance its maintainability. So again, a good example of the design evolution of a system, where as you evolve the system over multiple iterations, you can try and simplify and improve on the system as you go along. If we go on to the next slide, please. Jumping from a lab that we have at Teddington through to an end use of that luminous intensity measurement. So lots of acronyms here, so apologies, I will read this one because I will get it wrong otherwise. But the STARO GCSE, so spectroscopically tunable absolute radiometric calibration and characterization of optical ground support equipment. Takes a breath. So this is a system which allows us to do pre-flight calibration of satellite sensors from the UV into the sort of low infrared wavelength range. Now, the key thing here is that this allows us to take that SI traceable calibration from our primary standard radiometer at the NPL laboratories and apply it to the calibration of satellites at remote locations, wherever they may be. So in the bottom right-hand corner there, you can see this system being used at an Airbus facility down in Toulouse, calibrating a satellite before it was launched a few years ago. Now, again, the engineering applications of this are complex, so we're having to take that reference measurement from our primary standard and find a way of transferring it over to a remote location. We're also having to build a system to comply with some very strict quality standards. So an ISO 5 clean room, for example, and with Airbus and ESA as our customers, we had to make sure we were able to interface with their quality systems and other requirements for the space industry. But this again shows a real world application of the SI primary standard, because the pre-flight calibration of satellites is a vital step in actually being able to get usable information out of them. And I think that picture in the bottom right was for a satellite that would have been measuring methane or other greenhouse gases for an ESA mission. So these pre-flight calibrations allow us to perform a baseline on the sensor performance, validate the design of the actual satellite itself, but also importantly, perform the measurements around the uncertainty. We need to understand the uncertainty of that satellite, being able to measure it against a reference standard that we can apply from our primary standard. Now, doing this in a controlled environment with known sources gives us other options, like it gives you an insight into the likely degradation mechanisms, but also gives you a really good reference point then for your post-flight calibration checks afterwards. So again, from one extreme from our lab-based measurement to a very complex requirement on satellite calibration. If we go to the next slide, we can see how we apply the same idea to a different end user. So this is a project called Starwell, which has been a collaboration between NPL and RAL Space, where there's the same kind of need about the pre-flight calibration of satellites. But in this instance, it's a lot more around that new space sector. So, lots of smaller companies who want a quicker, cheaper, and faster calibration to a lower accuracy than ESA might in that last example. But this is again where we've had to look at the design and engineer a solution for that customer in collaboration with RAL Space. So things like simplifying the design, improving the portability, making it easier to break down and transport and reassemble, but also a lot of more basic fundamental things around tweaking the optical modeling to help us have better tolerances around the mechanical design, etc. So revisiting the design and the engineering to come up with a slightly different solution for a different customer base. So this has been a really successful collaboration with RAL Space and allows us to have that facility for small companies to get these quick calibrations of the mini sats and the smaller satellites in the space industry in the UK, which is extremely vibrant at the moment, to help us service that industry as well. So hopefully that gives you a really quick example of where we're trying to take that standard, primary standard for an SI unit, engineer that as a solution, but then also find ways of engineering and disseminating that measurement into different industries. I'd like to again thank especially Paul, Krish, Josh, and Aaliyah, who've been working on these projects for a lot. And thank you for stealing their pictures off their slide decks. But a really successful team effort between the science and engineering communities, but also importantly, with the end users, in this case, Airbus, ESA, and RAL Space. So I will stop talking there and hand over to Georgette, who can tell us about another example of what we do at NPL. Thank you.
So, hello, my name is Georgette Gaunt, and I'm an engineer at NPL. Next slide, please. So I started my 4-year apprenticeship in 2017. In year 1 and 2, I completed a level 2 and level 3 BTEC in advanced manufacturing engineering. In year 3 and 4, I completed a higher national certificate in mechanical engineering and a national vocation qualification level 3 in advanced manufacturing engineering and toolmaker and tool maintenance technician. Also part of that final year, I did an endpoint assessment, which led me to get my professional registration with IMechE as an engineering technician grade with IMechE. So with my apprenticeship, I had various aspects of engineering, including instrument making, mechanical, electrical, and general. As I chose to specialize in manufacturing engineering, I had the chance to use a large variety of machines, from a manual lathe to a turn mill. The skills I've developed over the past 8 years have helped our workshop manufacture and assemble components, from one-off items to large assemblies. A few examples of these are the differential absorption LiDAR, or dial truck for short, which is a mobile lab constructed from a 40-ton lorry, which was built to monitor atmospheric pollution. I also manufactured and assembled parts for the Star Wars project that Rob was previously mentioning. Alongside my apprenticeship, I also had the opportunity to inspire future generations, such as helping new apprentices and taking part in outreach events, showing young people what MPR does and what being an engineer entails. Next slide, please. So currently, I'm working with the Dimensional Metrology Group to provide nanoscale metrology. So this project entails developing an X-ray interferometer with the end goal of improving traceability of the meter. This requires developing the capability of ultra-high precision machining of silicon. The critical components of the interferometer are the 3 lamellae that I've got in the bottom left corner of the screen there, circled with a little red circle. So these lamella have to be, the critical part of the lamellae are they equally spaced. They have the dimension of 10 by 15 by 0.8 thick millimeters. With the high aspect ratio and thinness of the lamellae make the production very challenging. Alongside the machining of these lamellae, I've also experienced exactly how the machining I do changes the scientific research and measurement. I'm hoping by 2026 to have the working interferometer with detailed documentation allowing manufacturing of interferometers in the future. That's a very brief explanation of what I'm doing at the moment, but I could go on for hours otherwise. So now I'm handing over to Timothy. Thank you.
Thanks, Georgette. Good afternoon. My name's Timothy Camps, and I'm a senior scientist in the Advanced Engineering Materials Group at MPL. I'm also a chartered engineer and member of the Institute of Mechanical Engineers. Can I have the next slide, please? So I'm responsible for the delivery of friction, wear and lubrication, and this is an area of science called tribology. And really, I'm a specialist systems engineer relying on the expertise of my colleagues in physics, material science and chemistry to provide application-based solutions that are substantiated by these highly specialized measurements, which you've heard a bit about earlier today. With measurements of friction, we look to evaluate the performance of systems, whereas with measurements of wear, we look to analyze the lifetime of those systems. On the right-hand side, I've got 2 examples. At the top right, we've got solid particle erosion, where small bits of material are accelerated by a high-velocity gas jet onto pieces of material, where we evaluate the damage that occurs. And at the bottom right, we've got water droplet erosion. It's a similar style of test, but here water droplets impinge on a surface at high speed. And we use various microscopy and surface analytical techniques to evaluate the surface damage. Could I have the next slide, please? Tribology is all about interfaces and length scales. And part of the workflow of analyzing a problem is to look at which particular interfacial interaction is the rate limiting step, and then design repeatable laboratory experiments that reproduce that same wear mechanism that's seen in service in the laboratory, and then understand the failure mode. And this is all done to answer the question, can I have confidence that laboratory tests will correlate with real service performance? As an example of the different length scales, at the top right, I've got a scratch tester looking at the adhesion of coatings and scratch performance or scratch resistance of materials at the micron length scale. And at the bottom right is a reciprocating tribometer that evaluates surfaces at the millimeter length scale. While we do standard testing at MPL, which is useful for initial ranking of material during development, we specialize in bespoke engineering solutions that allow us to obtain specific rankings for real-world service performance. Could I have the next slide, please? So this slide explains my journey to deliver those measurements at MPL, and I started with an integrated master's degree in mechanical engineering accredited by the IMechE, and went on to do a PhD in tribology and several postdoc projects. From there, I had a portfolio and experience that allowed me to submit an application for chartership. And after gaining chartership, I moved to MPL, where I've been delivering friction wear and lubrication measurements since. I'll now pass on to my colleague, James.
Hi, I'm James Berry. Yes, next slide, please. Okay, so I'm a chartered engineer with the Institute of Mechanical Engineers, 20 plus years experience in mass and density measurement. So the photo on the right shows me presenting at an international measurement conference in Croatia. I'm responsible for the density calibration service. I've also introduced a Centre of Mass Measurements that's used for space satellite components and also some precision space-based physics experiments. So I'm currently heavily involved in a big project at MPL, which is the kibble balance project. So I'll talk a bit about that now. Next slide, please. So the kibble balance, so this is a method to relate mass. So this is a primary SI unit, the Planck constant. So it's developed at MPL by Brian Kibble in 1976, and it's now named after him. It's called the kibble balance internationally. Projects needed since 2019, mass is traceable to the Planck's constant instead of a physical kilogram artifact. And MPL is developing a next generation kibble balance. So this would be a more compact balance that maintains the high precision of existing balances, but is both simpler to manufacture and operate. And the image on the right shows you a concept of our next generation balance. Next slide, please. Okay, so this is where we're going from. So we want to develop a balance that has about 20 pp parts per billion realization. So you're talking about microgram level on measuring a kilogram. And so we have the previous kibble balance in the photo on the bottom. So this is based on an old 2-pan balance. It was hideously difficult to align the components precisely enough. You need to get angular alignment to within about 30 microradians. And it usually took about a week or so to actually align the instrument before you could do a set of measurements. What we want to go to is something more compact, which allows just direct vertical motion with no motion on the other axes or torques around them either. Our design engineers come up with a guidance mechanism that allows purely vertical motion and no motion around the other axes. This is the concept that you can see in the image on the right. Okay, next slide, please. Okay, so in my involvement with the balance, I managed to design, assembly and testing of several systems for the balance, the support systems, which include the main mechanical balance structure and frame, which you can see in the photo on the right. And also you can see, I moved to one side, you can see it behind me. So the actual physical balance is behind, I'm in the lab currently. I'm also responsible for vacuum systems, both the enclosures and the pumps that will mean it can operate in vacuum, gravity measurement, and then the external systems. And this includes, so the balance incorporates a number of very sensitive electronics, electrical components, and they need to be held at a specific temperature. So I'm responsible for those systems. And okay, and that's that's my presentation, and I'll pass back to Matthew.
Thanks very much, James, and all. Just a reminder to put your questions in the Q&A box, and we will get them in the next few minutes. Just a few things that came up for me there. With Timothy talked about tribology, reminded me that we do have a tribology group at the IMechE, if anyone is interested. And we have expert committees on all sorts of topics related to educational skills, transport, energy, every aspect of mechanical engineering. Mechanical engineering is so broad. We've got so many different committees covering all the different aspects. And if you're interested, go to our website and click on the industry and specialisms tab. And just a little bit about my role and what we do here. I'm head of policy at the Institution of Mechanical Engineers. So I work with our various members across the institution on different aspects related to engineering policy, including all the things I mentioned before, like energy and transport and educational skills. I'd like to ask Rob about the career development opportunities at MPL. What are the various routes in, and what are the sort of the pathways to be trained up and progress at MPL?
So you have the traditional routes. So we have, and Georgette talked about her experiences of the apprenticeship program. So specifically from the engineering side, we have a fairly rounded engineering apprenticeship side of things, but there's also measurement scientist apprenticeships and other types that we offer at MPL. This is something I think, as I mentioned, we do want to improve. So we are looking and working with some of my colleagues to see how we can expand that offering, offer higher level, like to zone level 5 apprenticeships as a minimum. We do have a graduate program as well. So again, this isn't just limited to engineering. There's a large graduate scheme for scientists who to get into the scientific areas. I should have checked when the closing date for those is, but I'm sure if you go onto the MPL website, you can find them. I guess the key thing in terms of the development side, though, is that somewhere like MPL offers you the opportunity to move and shift into different areas. So I don't think there's many people at MPL who haven't had the opportunity to be involved in other spheres of work or gain experiences in different areas. And with this idea that we're trying to build role profiles and career pathways for engineering and science and these other things, and trying to link that into any CPD that people want to do, you can join, start in one field and progress and move into different areas. And that's something we're very supportive of and want to encourage.
Thanks very much. I'd like to ask Timothy about his path to chartership. What did you find the process was like? What exactly the steps you took, and what did you find useful or perhaps challenging?
I think right at the start of my journey, I did a degree that was accredited by the IMechE. And so I'd heard presentations about possible routes to chartership from the edge of my undergraduate program. I think I'd stayed in an academic setting all the way up to before I moved to MPL, and there were some challenges around certain competencies in order to have a complete portfolio for the application. However, I found that actually IMechE was very supportive, running various workshops and sessions to illustrate how the opportunities that I could take in order to fill the gaps, if you like. And so I'd originally planned to apply for chartership about 18 months before I did, but with the guidance I got from the institution, I was able to fill those gaps and submit a comprehensive application. Yeah.
Thanks, Timothy. James, same question for you. How did you find your route to chartership, and what did you find valuable or challenging?
Yeah, I think it's well, you got a very big application form to fill out first of all. That's why you can't make the time to do that. But yeah, if you can get a lot of help from both the IMechE and staff at MPL to submit an application, so that's really helpful. And I find that although I work more probably as a scientist rather than an engineer now, it's actually both the IMechE and MPR supportive in getting to professional development and becoming chartered with their respective institutes. So there's a lot of support there to do that.
Thanks very much. Georgette has turned her camera off. I'll just check if she's still there. Georgette, you're a little bit earlier in your career, so maybe I'll ask you about the future. How do you want your career to develop over the next few years, and what sort of things do you think would help with that?
I think at the moment I've got a lot of opportunity to be involved in big projects like the project I was talking about, and just hope that I can continue to sort of help develop scientific research and continue to, I don't know, flex my skills and try different things and experience a lot of MPR lets us experience a lot of different like lets us use different machines all the time. We're not sort of one man, one machine sort of workshop. So just keep developing skills in different machines, different specialisms.
Brilliant, thanks. Yeah, so I began my career at the Rutherford Appleton Laboratory, so I'm familiar with RAL space. And I always felt sorry for my colleagues that worked on space projects, because often you'll design something for 10 years and then you strap it to a rocket and send it into space and hope that it doesn't explode as being sent upwards. Rob, do you want to talk a little bit about the challenges of designing things for space?
I guess to be clear, we're not designing the actual satellites, so that does provide a whole different realm of technical challenges. Where we are involved is trying to support and maximize the design efforts of the satellite companies. So, you know, in your example, obviously worst case is a rapid disassembly of their expensively built piece of kit. But once you launch the satellite, it's kind of there. There's not much you can do in terms of working on it or testing it, although there are some things we could talk about maybe later on that. So the more that you can fully calibrate and understand the system before it's launched, the more use you're going to get out of the satellite once it is launched. Now that isn't just the how accurate is it, or how accurate, or confirming the uncertainty of the measurements across a range of the performance spec of the satellite. Is trying to think, okay, if we launch this, it's going to get shaken around, it's going to be exposed to some extreme conditions and everything else. How can we perform enough on the ground to understand that if we start getting types of readings once it's in space, that we understand why that's happening? So I think that again is a sort of example which highlights how good engineering is incredibly creative. You're having to think, okay, what tests can we perform now so that if we get anomalous readings or issues in the future, we can understand them. The challenge in terms of that aspect of work that we would do for the space industry is not gold plating everything, I guess. So whilst you will have to build something to incredibly high quality standards and specifications and all the other things for the testing you're doing on some of the ESA projects, which are like 500 million satellite programs, how can you get a good enough result at a lower level for a small commercial startup that's launching dozens of shoebox size satellites as part of a different type of program? So it's that proportionality, I guess, which is key. And understanding that proportionality is something that cuts across what James, Timothy, and Georgette and everyone is doing, is that you can't fall into the trap of trying to do that, the most amazing engineering delivery you can that you could do for an ESA project, and applying that to the RAL space one. It's not bad engineering, by the way, it's just appropriate engineering. But the other is, the example behind James there, when you get to TRL 789 for kibble, it will need all of this quality and all of these standards. But at TRL 4 or 5, can you make do with something else to prove concepts, and how do you do that in a controlled manner? So I think one of the key skills that a lot of our scientists and engineers have to have at MPL is an understanding of proportioners, because that one person will work on it from TRL2 all the way through to TRL8, or somebody could be applying that science area around optical power and Earth observation. Those same principles and techniques can be applied to two very radical different use cases. So yeah, it's not just the complexity, but it's also that appropriateness and scaling of it for the space industry, Matthew.
Sure, thank you. Any of the other panelists like to add anything, or we have a question that is slightly related. So one of the challenges related to space, but then in designing the nanometer precision measuring equipments, what are the design considerations when you're working to those tight tolerances? Anyone want to volunteer?
Maybe if you repeat the question, Matthew.
Oh, sorry. It was what are the challenges in working to very tight tolerances like nanometers?
I mean, Georgette, do you want to use maybe some of the examples around the interferometer? Because I think in this case, Matthew, I think Georgette didn't mention that those lamella that she's manufacturing are on silicon, which is not the easiest thing to machine, but also it's machining those lamella so that they're in line with the crystal lattice of the silicon crystal, so that you can use the atomic spacing as your gratings in the interferometer. So maybe Georgette, do you want to talk about the fun and games you've had machining silicon?
Thank you. So when we first started this project, there was a big selection on what machine we were going to buy to start the machining. And then once we purchased it, we then still had to go back to the manufacturer of the machine to get things changed, to get things adjusted, to get things even things like getting more decimal points on the screen so we can see exactly what the machine is doing, and having to work alongside companies that don't really want to push the machine to that sort of level in some sense, to get the best we can from that. And then also working alongside the scientists to help with aligning the silicon, and using many different machines just to try and get the silicon aligned. And it's been a long project so far. I've still got a way to go, and yeah, there's a lot of I've only just brushed very gently on the top of everything I've been doing, but there's a lot of challenges. Yes.
Thanks very much. I'll come to Tim and James. I think so. Working at MPL, you must be working on the cutting edge all the time. I had the same experience of working at the Rolford Apple lab. You're always sort of pushing the limits. So, what are some of the engineering challenges that you've faced in the last few years of your career? Timothy first.
Thanks, Matthew. We've seen recently with the trend towards electrification in many fields, think about transportation, energy generation, and this has provided quite an interesting space for tribologists, some really challenges, because the environments that the coatings and the lubricants are performing in, and how they behave, particularly not just with their performance, but all the lifetime that can be expected out of them in these environments, are quite different to the traditional environments that they were designed for. So there's quite a lot of work that's going on in designing new instrumentation, and in particular in situ instrumentation, to actually understand the performance of these parts and materials. one of the great things about doing tribology at MPL, as I mentioned before, it's this interdisciplinary nature, but also with our being able to work with our engineering function as well to supply the various parts that we need, whether it's from the instrumentation part or the actual parts that we're testing. And of course, the preparation of those material samples has a really big impact on the quality of the measurements that we can make, right down to the surface finish as well as the dimensional tolerancing. And MPL can provide this beginning to end, if you like, wraparound on those measurements. Yeah.
Brilliant. And James?
Yeah, I mean, it's just, yeah, you're always trying to push what you can do really here. I mean, one example that can be quite challenging is that things that out in industry or other areas that they may have certain limits on what's acceptable. But for our application at MPL, it could be that that limit is far too high. So, for example, like the kibble bands behind me operates in vacuum. We need to have very low outgassing materials. The limits that NASA and EAST set for outgassing on their materials tend to actually be much higher than what's acceptable for us for our balance. So we actually have to do measurements ourselves on materials we're planning to use on the balance. That's actually to confirm we are getting outgassing levels that are appropriate for what we need.
Yeah, there was a question earlier. Just can you confirm, is that a kibble balance behind you?
It is, yes. That is our MPL's concept kibble balance, and be our sort of next generation balance, and which we're developing. So yeah, eventually it should become the UK's sort of national standard, providing traceability to the kilogram.
Brilliant. I must admit, I had to Google kibble balance when that came up in the chat. I wasn't familiar with it. There's a question in the chat, which is, MPL appears to have a good spread in regard to industries and markets. It supports quite diversified. Is a particular sector that you consider a growth area? And perhaps we'll go to Rob for that first.
I think it'd be hard to pinpoint one particular area as a growth area. I think what I could probably try and highlight is that we try to be responsive to the challenges that the UK has. You know, we're a UK laboratory where our aim is to improve the standard of life, and however you want to define that in terms of industrial strategies or other stuff, and respond to, but also inform on the government policy and a range of these things. And as there isn't one singular thing that's going to impact the UK, I think, you know, we couldn't single out one thing that we'd be doing. The ones that jump to mind, though, are things around engineering biology. You know, there's a big increase in, you know, the broad range of things that catchphrase could cover. The quantum program. So, you know, there's a huge amount of expertise in the UK in the quantum sciences. So I think the challenge now is how you take those innovations from quantum science, and you know, everything from quantum computing to, you know, new types of sensors and instruments, and how we build and capitalize from a sort of industrial perspective on those groundbreaking innovations that we had in the science. And then some larger programs around like things like timing. So MPL does a huge amount of work around providing disseminating accurate timing signals for a variety of applications across the UK, which you know some of the numbers you can throw out with these things are always fascinating. So you know, making the next generation, I mean, the current atomic clocks would only lose about a second of time, or be a second inaccurate over the 14 odd billion years the universe has existed, which is quite a startling accuracy. And there's a next generation after that to push it even further. So again, you know, it's the application of the science and those ideas to industry, to health, the healthcare sector. Again, really good example where we've done a lot of work with CR UK and others on how we can more effectively target treatments for health applications, how we can better treat cancer, how we can understand the different types of cancer cells, how we can provide apply that measurement science and technology to help tailor treatments for people. That's going to be a big thing in the future. Sorry, I ramble on here for a while, but even smaller things. So there's work we're doing around simple applications to be able to do better preemptive diagnosis of simple diseases like that affect an aging population. And then I guess the last one I'd flag is around data science and AI. So that's obviously a rapidly expanding field at the moment. But how can we provide that accuracy around, as a national lab around measurement, that however we're using the data and however we're using AI in that measurement chain or process or application still comes with that traceability and accuracy and reliability that's required to make decisions on. So yeah, very hard to pick one area, but I think all of those, whichever one it will be the biggest one that will increase our workload, but I think it'll be from one of those.
And I mean, everyone's talking about AI and how it's going to affect engineering now. Is NPL, your work, being affected by artificial intelligence yet, or do you think it will be in the next few years?
I think it would be inevitable that it will be in the next few years. What that looks like and how we can best react to it and also utilize it is one of the challenges we have. And it's in some areas like software, it's a lot more obvious and easy to see how the application of that would come around. But there's still obviously always going to be that place for people like Georgia or others and the skills that they've developed from the manufacturing space all the way through to assembly, test, or design. I do think that would be hard to replicate with AI. The experience that James and Timothy and others have is vital to that successful outcome. I guess the challenge is using AI in a way that complements that rather than attempts to replace or causes more problems than it brings.
Yeah. Anything else to add from panelists?
I just on the sort of on the AI point, we see quite a lot of use of machine learning techniques, and we find that we can use those and deploy those in the lab for different systems. A small example of this is in the work that I do, where I'm interested in where mechanisms occurring on surfaces, and we can use machine vision coupled with image classification technology to allow us to stop tests as soon as different wear mechanisms occur on the surface, and then investigate those surfaces using analytical techniques. So perhaps the techniques themselves aren't new, but maybe the power and the accessibility to using these techniques is now being realized, and we're seeing them deployed in the laboratory for materials evaluation.
Yeah, and Georgette, you're closer to education, formal education than me, certainly, or most of us. Have you noticed the rapid changes during the last few years in terms of the focus on data and AI and things like that?
My main experience of sort of the effects of AI is having my work checked to see if I've used AI to do my work. But whether or not, I don't think we've really got, well, it's been 8 years since I was at college, so a little while, but they weren't teaching it at the time I was there. But.
Yeah. So we put out a report a few years ago called The Future of Manufacturing Engineer, and we polled our members and IAT members to ask them what they think the skills of a manufacturing engineer would need in the next 5, 10, 20 years. And AI, mechatronics came up a lot, but interestingly, also communication skills and software skills, which we highlight with the IMechE and getting chartered, because some people have the idea that engineers are just robots, but we do need to work in teams all the time as well. I'd ask, we at the IMechE also talk a lot about the shortage of engineers and the shortage of skills. How do you find recruitment of engineers, and are there any particular skill sets that you think are lacking and hard to recruit?
I guess I can make a start on that one. I think the soft skills that you described there are a key thing. Is that you said there's a, especially for somewhere like MPL, where you don't have a production line, for want of a better word. You know, no one at MPL goes into work and does the same thing day after day after day. And as Georgette said in her example, you know, a lot of people who progress through like a mechanical apprenticeship program would end up working one type of machine continuously, running things where, you know, everybody in the mechanical workshop and the electrical workshop, they have to be able to do all the different techniques because they might get called on to do various things for various different projects. And those soft skills are really important there because, you know, that ability to actually really understand what's been trying to be done, to work within that team. We do a lot of joint ventures where, you know, we're working with other organizations to develop something. And also that, you know, that idea that, you know, there isn't a, you know, there's not a scientist in a room who sits there for 5 years scribbling away on a blackboard so he goes eureka and the problem's solved. You know, these days everything's solved by teams of people working together and, you know, approaching it. And that ability to communicate, that ability to work as a team, that ability to actually, you know, effectively listen, to understand and see different viewpoints is incredibly vital, especially at somewhere like MPL. Skill sets are hard to get. I mean, the practical skills are always valued. You know, people who've actually done hands-on work with things. But I almost look at it from a slightly different perspective as well, to say that it's an opportunity for us to train and develop people. You know, so again, I studied physics, and I've ended up working my way through nuclear engineering and, you know, working as the head of engineering for MPL. And the modern work environment, I think, is getting more and more, it's obvious to say it, but I think it's going to increase that more and more flexible, that ability to, you know, my dad was a shipwright apprentice and he worked as a shipwright for his entire career. You know, that's just not going to happen in the future. So you always need to embrace that and look at it in terms of how you can take the skill sets of people who might not be engineers and then help develop and utilize those in different ways to deliver things and give people that ability to jump careers. You know, again, obvious thing to say, but, you know, even more so in the future, you will be having several strings to your career. You're not going to be doing one thing for your whole life.
Yes, thank you. So we're almost out of time, so I'd like to take us back to the purpose of this this webinar, or one of the purposes, which was to launch a report and talking about the importance of measurement to engineering and importance of measurement to the UK economy. So I'm gonna go very briefly across all four of you. Maybe I'll start with you, James. Well, what do you see as the MPL's role and its importance, and the importance of measurement generally to engineering in the UK economy?
Yeah, well, it's very important. I mean, both from the traditional side. So you got some big engineering companies in the UK. So Rolls-Royce, for example, they still need a, you know, traceability for the thrust measurements on their jet engines. That all comes back to MPL eventually, and then sort of for more modern areas. So we've had people looking at wanting to look at the difference between additively manufactured components, which is a more new thing compared to how conventionally machined components are made. So yeah, there's definitely still a need for the traditional side, and that's the tough thing I think for MPL, to actually balance providing what it does for more traditional areas to where it has to move into the providing measurements for new areas as well.
Brilliant, thanks. And Georgia, do you have anything to add about the importance of MPL and what you see your role as?
I think the world doesn't stop developing, and measurement will continue to develop. I think that's very short and sweet, but
Yes. Okay, I'll go to Timothy, and then I'll let Rob have the final word.
Thanks. I think we're in the business of providing assured, traceable measurements that people can trust to make decisions. And as the world seems to be changing much faster than before, I think it's sort of important to communicate that MPL's measurement services are available to UK industry to help them solve problems. And so as we move forwards, we're continuing to develop our provision in conjunction with industry to meet those needs, as Rob said earlier, to help improving the standard of living.
Brilliant. Okay, Rob, final word to you. What would your elevator pitch be to the Secretary of State?
Oh, I'm terrible at those short, snappy responses, I'm afraid. I mean, I'd follow on from what Timothy said. There's no point us doing things in isolation and divorced from industry. We're here to support the country and its well-being and economy in whatever way you want to look at it. The challenge for us is to react to the changing industrial setting in the UK to support it in the best way possible. But I think also as well to help inform government. As a national lab, we should be helping DSIT or various parts of the government structure on how best to address some of the challenges that are coming. So some of the big things around, or high level things about energy. How can we support decision making around the energy mix for the UK? Autonomous vehicles, aging population and healthcare. All of these things at some point will distill down to measurement and confidence in that ability to measure something and make decisions on it, whether that's a policy decision or reassurance that an autonomous vehicle is going to be able to understand where it is well enough to not run over your foot or do something it's not supposed to be doing. So it'd be a very long elevator, but that would be my kind of pitch to the Secretary of State.
Yeah. So my own elevator pitch for the wider engineering community is, at the Institution of Mechanical Engineers, we have 110,000 members. And we have a wealth of expertise. So we offer ourselves up to the government to provide input to policy to make sure that they make policy based on good, sound technical advice. So we're just about out of time. That's our hour is up. I'd just like to conclude by thanking everyone for joining and viewing this webinar. Thank you to all our speakers. The MPL website is on the screen there, but if you'd like to get in touch, you can also get in touch with IMechE, which is policy@imeche.org, or at mplgov.policy@npl.co.uk. And a reminder that the report is available on the IMechE website. So thank you very much for joining us, and goodbye.
Thanks, everyone.